I mean, last year only, but after that we
Mhm.
had so many so many things, so many difficulties among us actually. So then we couldn't able to organize any sessions at that time. So now we started from Yagna sir last month.
Yeah, last week,
Last
last week, I think there was one.
yes,
I
yes, there
saw
was
that.
one. Yes, so now we are planning to restart our sessions.
That is very good.
Yes, yes. Thank you.
Yeah, I saw some of my colleagues also. They have given talks before
Hmm.
in this forum.
Yes, yes. Neeraj and then Debango, they are one of the like
Mm, mm,
earlier.
they have
So,
given.
mm.
Okay, sir, we are ready for live.
Okay, okay. Maybe, sir, you can share your screen.
Mm.
Mm, uh, I'll check once this. If streaming is happening. Sir, your slide is shared or
Is it not showing?
I can
Uh,
see.
oh, you can see, right? Oh, okay, okay, okay.
okay,
Maybe
just a
from
minute.
my
I'll
side there is some
share the
problem.
entire screen once again. Yeah,
Yep.
it's fine now.
Yes,
It's visible
fine.
for me, sir. Yes.
Okay, I'll check once this.
Not showing.
So we are live actually.
Okay,
Hmm.
I'll start. Then we'll start the session. Okay, so hello and welcome everyone to another session as part of our Assam Artificial Intelligence Initiative Technical Lecture Series. This will be the 36th lecture as part of this series. So today we are very fortunate to have with us Dr. Arkadip Roy, sir, who is an assistant professor at IIT Guwahati, and he'll be giving us a talk titled Robust Reinforcement Learning Algorithms for Task Scheduling in Mobile Edge Computing Networks. Little background about Sir. As I mentioned, he is an assistant professor at the Mehta School of Data Science and Artificial Intelligence at IIT Guwahati. Prior to that, he was a postdoctoral research associate at Coordinated Science Laboratory in UIUC, USA. Prior to that, he was a doctoral student in the Department of Electrical Engineering, IIT Bombay. His research interests lie in reinforcement learning, Markov decision processes, and resource allocation in next generation wireless networks. So, with that, I'd like to hand over the session to Argadip sir.
Thank you for this kind introduction, and thank you for inviting me, everyone. So now I will start my talk. Uh, so today's talk title is mm, Robust Reinforcement Learning Algorithm for Task Scheduling in Mobile Edge Computing Networks. So as the title suggests, you can see that we will be talking about reinforcement learning algorithm, which is one of the paradigms of machine learning. And in specifically, we'll be talking about something which is related to robustness. And we will see what does robustness basically mean in this context. And this kind of algorithms we are developing for task scheduling in mobile edge computing network. All of you might have heard about this now, that as a like part of 5G or 6G communication system, this mobile edge computing has been a big contributor in that. And in such a network, how we can schedule certain tasks, different tasks that are arriving using this kind of algorithms, that is the thing that we will describe today. So this is the brief outline of my talk. First we will give an introduction and followed by motivations, and then we'll describe the system model. And there are two piece of work. First is this robust and low complexity task scheduling algorithm uh, that I will describe, and then after that, if time permits, we will briefly talk about robust learning algorithm also. The system model is kind of common for both this work. So I'll first present the system model, which is sort of common for both this, and then we will go to the individual works, and then I will conclude the talk. So, as we know, in today's wireless IoT systems, there are resource constrained nodes in terms of uh, computation and energy. So, what does it mean? Basically, in wireless IoT systems, these nodes do not have enough power in terms of computation energy. They are constrained in terms of computation. They have limited computation power. The amount of energy that you can spend in a node is also kind of finite. And there is a constraint on these also. However, in next generation wireless networks such as 5G and beyond in 6G, there are many IoT applications. These are many very much resource hungry. So they take away a lot of computation and energy and so on, such as critical IoT, extended reality, massive IoT, and etc. So in this kind of systems, it is very important that we manage our resources efficiently to have a sustainable solution, or in other words, to have a green solution which can look into these aspects. Because when I talk about green networking, then how my energy should be spent, what should be my power consumption, how much computation power we should allow, this kind of things becomes very critical. So there are standardization efforts where there is an emphasis on energy efficiency, as well as this multi-access edge computing or mobile edge computing that has also become popular. So 3GPP, which is a standardization body for 5G, 6G communication system, in 3GPP's release 17, this multi-access edge computing or MEC systems has been standardized. So MEC system is some kind of you can think of it as some kind of a cloud system, but the cloud is located closer to the user. Therefore, we can make quick decisions possible at edge. So it's not like we have to wait for a long amount of time by submitting my task to the cloud and wait for the result. But it is a cloud which is closer to the user. Therefore, it gives fast decisions. Also, there is a focus towards usage of machine learning techniques for RAN, radio access network, or automation, which is a part of 3GPP release 18. So in 3GPP, in their release 18, they have talked about this. So therefore, it will allow us to do a better resource management by utilizing machine learning for automation tasks involved in RAN. And in this talk also, we are going to see that we are talking about some kind of automation, and and how we can use ML to do that in a MEC system. Uh, that will be the one of the agenda of today's talk. So this is the system which looks like this. So there is an MEC server, and these are my IoT nodes. Okay, so now you can imagine it as for something like a, let's say, there is a big smart city where there are various entrants, and there are many face recognition entities that are present in these entrances. So this face recognition task, these are being handled by IoT nodes. Now what you can do is either you can do this task at the device itself, or you can send it to the MEC server which are installed nearby. Now, what is the trade-off involved? If you do it locally, then typically computation power is less, because they are equipped with low-end CPUs. However, the delay is typically high because the computation power is limited, so delay is high, and therefore there is a chance that it may violate the deadline. I mean, it could happen that there is a deadline associated with your face recognition, and the deadline could be violated because these are these are low computation power, so it will take a lot of time to do that. On the other hand, if I do it in MEC server, so if I offload the task over the air to the MEC server and do it here, then the power consumption becomes high because they have high-end CPUs, so it will consume a lot of power. But at the same time, the delay will be small because the CPUs can process this task in a faster manner. Therefore, the chances of deadline violation are less. So therefore, you can see that there is a trade-off between doing the task here versus performing the task at MEC server. Okay, and we are going to cater to this trade-off. So what kind of system we're considering? We're considering a random arrival of task. Means tasks are arriving at the devices or the IoT nodes in a random manner. And there is a soft deadline, by which I mean that I can allow some amount of deadline violation, but that has to be limited. So the expected amount of deadline violation has to be less than some bound. And the channel condition of the nodes with respect to MEC server is also random. The channel condition means when I send the data, it may take long time or less time or more time depending on the channel condition. If the channel condition is good, then it may reach quickly. If the channel condition is bad, it may reach with more delay. So this channel condition is also random. I mean, for our case, we have considered it with some probability it is good and some probability it is bad, more like a Bernoulli distributed random variable. Okay. So now what we want to do is we want to do average power consumption subject to the minimization of average power consumption minimization subject to a constraint on the deadline violation. If we want to do that, then this kind of problems can be formulated like a constraint Markov decision process. So it's a constraint problem because we want to minimize the power consumption, but there is a constraint on the deadline violation, so it becomes a constraint MD. However, what is the problem with this kind of solution is this kind of solution does not have the robustness, and that is the main motivation behind us for considering this kind of thing. Because if I solve the CMDP and find out the solution, that solution may not be robust. So, what I mean by robust is, let's say, if I x-axis is lambda, which is the arrival rate of the task, and y-axis is the power consumption. So it may happen that I have optimized my system for lambda equal to 1. But when my lambda becomes 1.1, then what will happen is the power consumption might become very large. So it may become something like this, that this is my lambda equal to 1, and I have optimized for this point. But if there is a little bit perturbation or sudden shift of the value of lambda, then your power consumption drastically increases quickly. So therefore, this is not a good solution. It lacks robustness. Your solution is not robust with a variation of under the variation of lambda. If I change the lambda or the arrival rate little bit, then your power consumption suddenly shoots up. So it is optimized for a given value, but it may not work for some other value. And that is unavoidable because in practical setting, it may happen that there is a there is a small shift of the arrival rate, or with time there is a small perturbation in the system. Those kind of things may occur. Therefore, if I do this traditional constraint MDB based solution, they are not robust enough. I am interested in a solution which might give me something like this. So instead of this, what I want is, let's say, something like this, where I don't care whether, I mean, if it is little bit worse than the optimal at lambda equal to 1, I am okay. But I want a flatter solution, which will kind of not fluctuate much, even if there is a small change of lambda. That's what I call as robustness. So by robustness, what I mean is I want a solution which will uh, not like which will not become very worse if there is a small perturbation in lambda. What I want is a more flat kind of behavior, that okay, even if there is a small shift of lambda, my power consumption is not increasing too much. The slope is less. I want that kind of solution. Why I want that? Because it talks about green networking. If I talk about green networking, then these kind of solutions are more green because it gives you a stable solution. It gives you a stable solution under within a range of arrival rates, rather than the first case where it is with small increase in lambda, my solution become quickly degrades. Okay, so that is the motivation. Moving on, if there is any question in any point in time, please feel free to ask.
Okay, sure.
Yeah. Okay, so what is the motivation is, first of all, high sensitivity to changes in system parameter that I just described before, that if there is a small shift in my lambda, then the solution becomes highly sensitive, and it quickly goes like this red curve. I don't want that. So therefore, this is one of the motivational shift, that I need to use a robust formulation to the distributional shift. So distributional shift means there is a change in the value of lambda. And if I and this is one of the challenges. And other challenges are because if I use like traditional methods for solving CMDP, there is a cost of dimensionality. That means if my number of states or number of IoT devices increases, then the complexity becomes higher. So I need to use some low complexity algorithms. Also, there is a cost of modeling because the computation of optimal policy using the CMDP will require me to have a knowledge of underlying parameters. That knowledge may not be present. Therefore, we need to use model free methods. Okay. So these are some of the motivations which will which we will cater one by one in this present work. So my main target is to use robust formulation so that even if there is a small shift in distribution, I may be able to tackle that. My solution should not be fluctuating too much under the variation of this system parameters such as task arrival rate or channel statistics. Okay. So this is the kind of scheme, kind of application area that we are looking into. So it might be a smart city kind of solution, and these are my MEC servers. These are connected to some base stations. Okay, so this is my system model. I have IoT nodes. These are my IoT nodes. This is my MEC server, which is connected to a base station, and or we call it AP. And these are my assumptions. So there are some task arrival that is happening at these IoT nodes following a Poisson random variable with parameter lambda, and the service time of task is exponential with parameter mu. So the tasks are arriving at a Poisson random variable, that is the arrival process, and the service time means the amount of time a task spends in the system is exponentially distributed with parameter mu. And we are considering licensed frequency band. Licensed frequency band basically allows me to do a centralized control, centralized distribution of resources by the MEC server. So it is basically that MEC server is taking the decision, and it has knowledge about everything in the system whenever there is an arrival and departure, so on. And this the centralized guy is making all the decision. Okay, so it is working in licensed frequency band, which is like, for example, 5G or 6G kind of bands. Channel condition, as I said, it can be a Bernoulli distribution, either it's good or bad with some probability. Okay, so this is a probabilistic system. My task arrival also happening following a random process. Service time is also exponentially random variable, and channel condition is a Bernoulli random variable with good or bad with some probability. So now this is my state space. Okay, so what is the state space? State space is I, which is the number of local tasks. Because whenever a task is arriving, I need to make a decision. What I can do, I can either do it locally or I can do it here, right? And also the channel condition is also associated with it. So now in the state space, we consider this I, comma jg, comma jb, comma e. So what is I? I is the number of local tasks. So at present, what are the number of local tasks? How many tasks are executed locally? At present, how many tasks are executed at the MEC with good channel? At present, how many tasks are are getting executed at the MEC which has a bad channel? So these are JG and JB, and E stands for event. So event can be, for example, there could be an arrival of task, there could be a departure of task at any given point of time, because as I mentioned, these are following some random variable. So these are my events. So if there is an arrival, then E is equal to E1. If there is an arrival with good channel, if there is an arrival with bad channel, then E is equal to E2, and so on. So this is my state space. Now, state space has certain constraints. These constraints help us in making the state space finite. So I is less than equal to N1 and JG plus JB less than equal to N2. It basically means that this is the number of this is the limitation on number of local tasks, and this is the maximum number of MEC tasks. Okay. And these are my action space. So action space is A1, A2, A0. A1 means I will do it locally. A2 means I will offload it to the MEC. So I will do it at the MEC server. A0 means staying idle. So whenever there is a departure, I will take A0, which is basically staying idle. And whenever there is an arrival, I will either choose A1 or A2. So these are the typical events that, okay, there is an arrival. It may be with good channel or bad channel. There may be a departure. So during arrival, I either need to do it here or I need to do it there. During departure, I don't do anything. I stay idle because nothing, no other action is involved. Now, depending on my state and action, there are certain costs. Okay, so when I talk about reinforcement learning, everything is based on that I choose certain actions, I get some cost or reward, and then I try to maximize the reward or minimize the cost. So here there is something, a power consumption cost, and it is like this. So these are, I mean, nothing to worry about these formulas. These are standard formula which are like what will be the power consumption if there is a computation. So that is Wi Fy cube. So W is a coefficient and F is the frequency. Okay, this is a standard formula. And for offloading, what we are saying is POB means power consumption if the channel is bad, that is D times POG, that is power consumption if the channel is good. So D is a channel degradation factor. So it might be like, okay, if the channel condition is bad, then I require two times the power that is required if the channel condition is good. So in that case, D will be equal to, and this is my cost rate. So depending on my state and action, if my number of users are I, JG, JB, so I local users, JG users at the MEC with good channel, JB users at the MEC server with bad channel, then this is my power consumption. So PCI is the power due to computation at the local multiplied by I plus 1. PCM is the power consumption at the MEC server multiplied by number of users at the MEC, and this is the offloading power last. So JG and D times JB, because for bad channel, my power is D times that of the good channel. Okay, and this is about the power. And another metric that we talked in the beginning, that is deadline violation, right? So we need to give a cost related to deadline violation also, and that looks like this. So deadline violation is BC divided by FI, where B is the packet size, number of bits, C is the CPU cycles to compute a bit, and Fi is the CPU frequency. This is also, again, this is a standard formula, so no need to worry about it. And this is BC divided by FM. So this is the cost for MEC execution, and it gets multiplied by JG plus JB because these are the number of users. So this is like a shared resource. So that's why the computation time gets multiplied by the number of users that are sharing the MEC. But local is more like individual resource, so there is no sharing. And B by RM is the task offloading time, where RM is the channel capacity. Okay, so RM is the channel capacity, that how much data rate maximum it can support between the IoT device and the MEC server, and B is my number of bits per computation. So if I take all these things into account, then this is my deadline violation. So through this formula, I calculate what is my total delay because of in the current state, and then if the delay is greater than L, where L is the deadline, let's say it is 1 millisecond. So if the total delay in my current state is greater than 1 millisecond, then I say that cost is 1, otherwise it is 0. Okay, I mean that means basically if it is greater than L, then there is a deadline violation, otherwise not. Therefore, this is the cost. So it is basically an indicator function, which is when this condition is true, it is 1, otherwise it is 0. So this is my deadline violation cost. And depending on my state and action, I will also move to a new state, and that is kind of written in this manner, that from state S I go to state S dash with this much probability under action A. So this is the notation, and these things are functions of lambda and mu. Remember, lambda was the arrival rate, mu is the service rate. Okay, so so transition probability are functions of lambda and mu, and I mean this is the system model. Okay, and P is the transition probability matrix, which is a matrix of size S cross S. I mean mod S cross mod S, where S is the state space. So it is basically a matrix. So size is number of state times number of state. I mean number of rows is number of states, number of columns is also number of state. So from any state I can go to any state with some probability under certain actions. Okay, so now I am interested in finding a policy. Basically a mapping between state and action. So I need something like a table which may look like this. Let's say this is my state, and this is my action. So when I am in state S1, I will choose, let's say, A1. When I am in state S2, I will choose A2. When I am in state S3, I will choose A1, something like this. So this is a particular policy. Okay, and I want the optimal policy. Means there will be many such policies like this. Let's say A1, A2, A1, A2, A1, A1. I mean, I'm just showing for 3 states, but here the number of states are more. So for each state, there can be an action, and this table is my policy, and I want to find out the best table, which will give you the optimal policy. Okay. So this uh, talks about the system model. If there is any question, maybe this is a good time to take some questions before diving into the first work. So this was the kind of basic common information. So if there is any question, I can take now some of them regarding this model.
Sasanko, I think, Vigyan, I think one question in YouTube chat box, I only ask, maybe you can. So just I'll only ask, sir,
Hmm.
how to define the trade-offs between robustness and convergence speed?
Robustness and convergence speed.
Speed here.
Okay. Okay, I think this question I will take at the end, because this is,
Maybe yes, yes.
yeah, because this is when I describe the solution, then it will be clear.
Oh, okay, fine.
Okay, so if there is no other question related to model, so let me proceed, and then I will answer this question towards the end. That will be a
Sure,
good point.
sure. Oh, okay.
Okay. So now moving on to this algorithm part, where we will talk about the robust and low complexity algorithm for mobile edge computing, and this work has been accepted for publication in IEEE Transaction Green Communication recently. Okay, so as you have seen that using dynamic programming method, I can find out the optimal solution, which will depend on the state transition probability. So this is my state transition probability, right? And it's a function of lambda and mu. So therefore, using dynamic programming method, I can find out that what will be the optimal solution. However, it will depend on lambda. And the problem is this lambda might change with time, and it may be difficult to know lambda. Okay, so what I do, I say that okay, the optimal solution is also sensitive to task arrival rate, because as we have seen in the graph that as I increase lambda, my optimal policy, which I find by solving the MDP CMDP, might perform like this, that the power consumption is very sensitive towards changes in lambda. Okay, so I don't want that. Okay, so optimal policy is sensitive to task arrival rate. Optimal solution for lambda does not work well for lambda plus epsilon. So if there is a small change epsilon, then my earlier solution does not work well. Therefore, there is no robustness towards distributional shift. Therefore, we need a solution which will work well over a range of lambda. So instead of a particular value of lambda, I am interested in optimizing my solution over this set. Okay, so earlier I was working with this nominal lambda. Now what I say is I will try to develop a solution which will work for this range of lambdas within a set that I call as uncertainty set. So within this uncertainty set, I want to optimize my solution. So in the literature, there are three kinds of algorithms that are there. One is called this Lyapunov-based optimization. However, there is a trade-off of order of V over order of 1 by V. So that means if I'm order of V close to the objective, then I'm 1 by V close to the constraint. So that means objective and constraint cannot be close together. So that is the one of the problem with this approach. And now there are two other approaches. So first one is MDP based, where I will assume that I know this nominal lambda and the uncertainty set. So here I'll assume that I don't know lambda surely, that what will be my value of lambda, but I know that it will lie within this set. For example, I don't know that lambda is equal to 1, but I know that lambda is between, let's say, 1 to 1.5. Okay. And third one is an RL based technique, that is robust RL. So in this case, I don't have any knowledge about the nominal lambda also. So I just know that lambda will lie on certain range, but I don't need to know nominal lambda also and uncertainty set also. But I just need to know that, okay, there is a set within which the lambda will lie. Okay. So first we are going to describe the robust MDP part. Okay. So what we do is we propose a robust CMDP formulation. Earlier we said that if we just do CMDP based, then this kind of plot may be obtained. So what I do is we try to formulate a robust CMDP that will minimize the worst case total discounted power consumption, and then there is a constraint on the worst case total discounted deadline violation. Just you have to focus on this worst case thing. Earlier in typical formulations, we talk about minimizing total discounted power consumption subject to a constraint on total discounted deadline violation. However, now we are talking about the worst case, which basically means that I'm taking the worst thing that could happen within this uncertainty set and trying to optimize against it. Okay, so it's basically something like this, that an interpretation of this is something like this, that nature is kind of playing a game against me. So nature will throw us a lambda which may be very bad for me, and I need to make sure that my solution is optimized for that worst scenario. And that's why I write this, that minimize the worst case total discounted power consumption. Now, if we do that, then what will happen is our solution is already optimized for the worst case within this set. Therefore, if my lambda is little better than the worst case, then it will not perform bad. So therefore, this kind of solutions will show robustness. In other words, we will kind of get a plot which looks something like this, that it will be much flatter as I change lambda, because this YOLO solution is already optimized for the worst case, not for a given value of lambda. That's the motivation. Okay. And for that, we have proposed some algorithms, and we have shown that almost robustness with almost no additional complexity. So to answer the question that was asked a little bit ago, that what is the uh, mm, like about the convergence and robustness, what is the trade-off? So it's basically this robustness we can incorporate with no additional complexity. So complexity wise, we are not too bad. I mean, there is only small additional complexity that comes because of robustness, and because of this small amount of complexity, the convergence will be slightly worse, but not too much bad. And how much bad, that will also show in the next slide. Okay, and after that, we propose some low complexity robust heuristic also that will cater to this high complexity, and then we implement these solutions in NS3, which is a network simulator, which is a practical simulator where we can implement this kind of solutions. So as I said, that is a robust CMDP, or what we call as R3 CMDP. Basically, it is robust return, robust constraint MDP. Okay, so this is the nature which is throwing at me the worst case. So nature is throwing the worst power consumption, worst deadline violation, and I am trying to minimize over the actions subject to this deadline violation constraint, and that is my objective. So this is nature which is throwing at me the worst lambda that is giving me the worst power consumption and worst deadline violation, and I am trying to minimize over actions corresponding to this scenario. Okay, so CMDP based policy performs poorly whenever there is a small change in lambda, but in R3 CMDP formulation, we are robust in terms of objective as well as constraint. So this is my mathematically, this is my objective function that I am trying to minimize over the worst case. So this entire thing is kind of worst case. That max, sorry, let me change the color. So this is the worst case power consumption. There is an integration because it is continuous time in nature, and I'm trying to minimize over this. Similarly, this is the worst case deadline violation, and trying to find the trying to make sure that this worst case deadline violation is less than equal to constraint. Okay, and these are some Bellman equations that I can write down. I mean, Bellman equation exists for normal optimization problem, I mean normal MDP, and here we have a robust MDP. So these are my Bellman equations for this robust MDP. So this is the cost plus gamma times the expected value function. This term is extra, that is coming because of this robust optimization. I mean, if you look at a normal Bellman equation for MDP, then this max operation will not be there. Similarly, here also there is a max that this equation is to handle the constraint. So here also there is an extra max operator. Traditional Bellman equation does not have this. Now, these are some of the results that we can prove in this context. It says that the Bellman operator, this Bellman equation that we can show, this Bellman operation, if I do, then this operation is a contraction mapping. Basically, this is a great result that basically says that if that means if I take 2 points and allow this Bellman operator to act on it repeatedly, then the distance between the points become lesser and lesser, right? See, now what is the meaning of this equation? That T max pi, this is the Bellman operation. I am applying on V and I am applying on W as well. So after the application of this Bellman operation, the distance between the points is less than equal to gamma times the distance between the original points. So basically, if I keep doing that, then my points will become closer and closer, and ultimately it will converge to something called fixed point. So there is a convergence to a fixed point, which is given by this, that basically it says that if you apply this operation again on this point, you get the same point. So because of this contraction mapping, we can design an iterative scheme that will allow me to converge to the fixed point, and the fixed point is nothing but the optimal value function. Okay, we are interested in the optimal solution, and because of this property, it allows me to design an iterative scheme. Means iteratively I am changing the value function, and finally I will converge to the optimal solution. Okay, and this is the result which will allow me to write the algorithm that we are going to present next. So therefore, because of this result, we can use the robust value iteration scheme. This value iteration scheme is the scheme that is used to handle MDPs, and since we are dealing with robust MDPs, we will use robust value iteration scheme. And to handle constraint, we need another additional thing, that is just like a gradient descent approach to handle constraint. So what we are going to do, to find the optimal value function, we are going to design an iterative scheme, which is nothing but this robust value iteration that will allow me to converge to the optimal value function. But there is a constraint associated with it. To handle the constraint, I will update my Lagrange multiplier following this gradient ascent rule. Now the question is how difficult the problem is, right? Because now we have introduced a robustness. So because of this robustness, what will be the additional thing that we need to do? So this result basically says that for this paper we are considering an uncertainty set. If you recall, we have talked about an uncertainty set, that my lambda will lie within some set. So what is this set? That is defined in this manner, that uh, the x and x naught, if I take the KL distance, so d is basically the Kullback-Leibler distance, then the distance between the x and x naught is less than equal to u. So it means that if I take the lambda, nominal lambda, and take another lambda dash, let's say, then this nominal lambda and another lambda dash, the KL distance between these two probability distribution with lambda and lambda dash should be less than equal to u. Okay, and this is a standard model for uncertainty. So this model we are taking, and uh, under that, my optimization problem that I need to solve additionally for the robustness, it becomes like this. Okay. So this is my additional problem. This is rho tilde equal to max over p dash p transpose b, which is nothing but this. If you look at this expression, this max over expectation, this expectation is basically this p transpose. From expectation only I am getting the p transpose b. So basically I am saying that if I want to solve this problem can be written down like this, that it is max over p tilde p transpose b, and we can prove that under this uncertainty set, this problem can be reduced to a one variable convex optimization problem. So our life is good. This problem is a convex problem. The additional problem that I need to solve because of this robustness is a convex problem. So therefore, it can be solved using bisection method. Okay. So now this we have proved. The proof I have not given here. If you are interested to look at the proof, you can please go to the paper where the detailed proof is there. So therefore, no need to look at this complicated algorithm. Just the flowchart. You can refer to the flowchart that I am saying. So what I will do is here for a fixed beta. So beta is my Lagrange multiplier. So what I will do, I'll first fix the Lagrange multiplier, and then I will perform the robust value iteration. So robust value iteration has two things. One is the normal, usual value iteration, and then inside there is this robust. Because of this robust, I need to solve this. Now this I am going to solve using bisection method. So bisection method, you try to solve the inner problem, and then you solve the robust value iteration, and then you update beta following this gradient descent. Okay, so this is the algorithm. So what I'm doing, I'm solving a constraint problem. Therefore, definitely there is a Lagrange multiplier that I need to tackle. So that I will handle using gradient descent. And then for a given beta, if I fix my beta, then my problem is a robust MDP. So there is two part. One is the MDP for which I need to do the value iteration, and to handle the robust part, I need to find this bisection. Using bisection, I need to solve this. So together, this is my algorithm, and whatever is written in the left side is basically the summary of that is in the right side. Now, compared to traditional MDP, the inner bisection has an accuracy of order of log of 1 by epsilon. Because if I need epsilon accuracy, I need log of 1 by epsilon steps to solve the inner problem, this robust problem. And then therefore my total complexity becomes a square log of 1 by epsilon square. So what is happening? If you look at a traditional MDP, then this value iteration, it requires this many computation. Log of a square s is the state. So mod of s is the number of state. A is the action space. So mod of a is the number of actions. And then sorry, there is no log. Then this is log of 1 by epsilon for epsilon accuracy. So if I need epsilon accuracy, I want this many number of this many order of this kind of uh, iterations I require for convergence. That is for a normal MDP. Now we have a robust part. So that part is being solved inside, right, this problem, and this can be solved using order of 1 by epsilon. So that gets multiplied, and finally for this RMDP or robust MDP, we get this extra factor, that is a square a, and then instead of log of 1 by epsilon, we have log square, because the additional inner robust problem requires another log of 1 by epsilon. So this is the total complexity. I think now I have answered that question more clearly, that because of the robustness, this additional instead of this, there is an extra log of 1 by epsilon factor that is getting multiplied for the computation. So you require this much of computation for the robust MDP, and this so log of 1 by epsilon is the extra factor that is coming into picture, which is not too bad, because if I make, let's say, epsilon equal to 10 to the power minus 4, then the log of 1 by epsilon is log 10 to the power 4. So it's basically like 4 times. So because of this robustness, my computation increases by a factor of 4 if my epsilon is 10 to the power minus 4. Okay, that's the answer. Okay, moving on. So the problem with this approach is, again, we are not fully satisfied with this result, because still there is a dependence on order of a square, right? If the number of state becomes large, then this a square also could be very large. So is there a way to reduce it further? So for that, we propose this robust heuristic. It says it is something like this, that when I solve the problem, we kind of find this kind of structure, that this is the structure of the optimal policy. So as I increase my value of I, it initially the probability of MEC execution is 1. So most of the task, all the task goes to MEC, then it goes to local, and then again goes to MEC. So it is kind of said a double threshold structure, and that's an observation we have got. So when I write the algorithm and let's say compute it in MATLAB or Python, then I get this kind of policy that as a function of I, if I increase the value of I, then first the task will go to MEC, then all the tasks will go to local, and then again to MEC. It's kind of double threshold structure. Now, what I'm doing is I am interested in a solution that will retain this robustness, but at the same time I don't require the knowledge of lambda uncertainty set. So that will allow me to propose an algorithm which will kind of not suffer from the curse of modeling, and it can be implemented online. Okay, so what I do is I I take this as an observation, and I approximate this using this. Okay, so this is the kind of curve that I am getting, double threshold policy, and I approximate it like this. It's like a sigmoid, collection of two, addition of two different sigmoids, and then the algorithm that I get is something like this. Becomes very easy based on this, that whenever the deadline is, so look at line number 7, whenever the deadline is almost violated, then I just select action A2, that is MEC execution. Otherwise, I select action A2 with probability FEI plus GEI. So FEI plus GEI is basically these values, I mean, based on the approximation. Otherwise, I choose the other action A1, which is the local execution with remaining probability. Okay, so the algorithm is very simple. What I do is I need to store these values FEI and GEI, and based on these values I say that okay, I will choose the MEC execution with the probability FEI plus GEI, and with the remaining probability I will choose local execution when my deadline is not, deadline is not violated. But when the deadline is close to violation, then I just select action A2, because then I can ensure that deadline is not violated. So now comparison of these three algorithms. The first algorithm is the one that is for the CMDP, no robustness. Here the storage complexity is this much, computation complexity is this, and the online feasibility is not there. It cannot be implemented online. I need to solve it offline, because it will require me to have the knowledge of lambda and the uncertainty set. Second algorithm is the algorithm that is proposed by me, proposed by us. So in this algorithm, our storage is this much and computation is this much. As I said, there is a increase in the computational complexity log of 1 by epsilon. This is also not online feasible. Third one, that is the heuristic approximation based that we proposed. So in this case, the storage is order of n1, because I just need to store the FEI and GEI for all values of I. So storage complexity also reduces. Computational complexity order of 1, because each time I am just looking at the value of I and these probabilities. So based on the probability, either I choose A2 or A1. So it's basically order of 1 computation, and also it is online feasible. So therefore, in the last algorithm, we have kind of retained the robustness, and the computational complexity is also not too much. I mean, really good compared to the other one, the order of 1. So these are some of my numerical results. Basically, if you can see, this is kind of the plot of the double threshold structure. So this diamonds and plus, these are like change of, so plus belongs to, plus means it is MEC execution, diamond is local, and so it is this kind of structure. And if you look at this plot, this is important, that if you see the CTSA is the algorithm without robustness, you see the it goes very fast. This is relative power consumption. It increases very fast, whereas the second one, the algorithm that we propose, the relative power consumption increases much slowly. And therefore, like it has more stable behavior or more robust behavior as I increase the lambda. So even if the lambda is changing, my power consumption is increasing at a slow rate. And deadline violation constraint is made for both the cases. Some more results. These are some simulations done on NS3, which is an open source network simulator. And there we have done the solution for this narrowband IoT system. I mean, it's a open source code that was there, and we took the code. It was developed by some Belgium university, and then we customize it, and then implement our algorithms, and we see that compared to other algorithms, still our algorithm performs well. So to conclude, the trade-off between the power consumption and deadline violation we have considered in this work, and we have incorporated robustness. Optimal task allocation, what we did in the first algorithm, it gives you the optimal robust solution. However, there is an additional complexity which is by a factor of log of 1 by epsilon, and therefore what we do is we we saw the need of decreasing the computation further. So using the double threshold structure, I presented a robust heuristic that gives me huge reduction in storage and computational complexity. And so that brings us to the end of the first work. If we have some more time, maybe quickly I can cover the second work also. So
Yes, sir. It's fine.
you have time?
Yes.
Okay.
Okay. Fine.
Yeah. So this was about MDP, robust MDP. So in this case, we have assumed that uh, if you look at this, I'll go to this diagram again. That there is a nominal lambda and uncertainty set. So for these algorithms, for the first algorithm to run, we need to know that lambda is belonging to, let's say, 1 to 1.5. That kind of knowledge we need. So I don't need the exact value of lambda, but I want to know that in which range I basically which range lambda lies. But for the second work, we don't even need that. We just need that, okay, lambda lies within a uncertainty set, but we don't need to know that which uncertainty set. I mean, what is the nominal lambda, and what are the endpoints of the uncertainty set. Nothing is needed. We just need to know that there exists a structure like this. Okay. So this work also is published, accepted recently in IEEE transactions on green communication and networking. So this is a work with my PhD student, Vicky Masi. Okay, so coming back to the same diagram, uh, where we talked about robust MDP before. Now I talked about robust RL. So in this case, again, this is the problem formulation already you have seen. The only change is we're just considering min-max here. So in the objective function, so instead of R3 CMDP, we are solving a R2 CMDP. So we are robust in terms of the objective function, and we try to meet the constraint. Okay, rest of the things is similar. Now this also you have seen that if I know everything, then I can solve using this manner. That for a fixed beta, you solve the problem. Beta is my Lagrange multiplier, and then I use gradient descent to update beta. Now in the learning setting, there is a problem, because in the learning setting, I cannot really solve the problem for a fixed beta, because my transition probabilities are unknown. I don't know the lambda, mu, all these values are unknown to me. I don't know the nominal lambda, I don't know the uncertainty set. So this is the way I can solve it in the MDP setting, but not in the RL setting. So in the RL setting, what I do, I construct an uncertainty set using R contamination model. So if you are interested to know more about the R contamination model, you can refer to this paper. So in the R contamination model, it says that PSA is my kind of that nominal lambda that has a weightage of 1 minus R, and then there is R plus R into Q. There is another, there is weightage R on the value Q, which can be a random variable. So what I'm saying is, if I make R equal to 0, then what will happen? Then I will get PSA, which is basically nothing but the that nominal lambda. So if I make R equal to 0, then it becomes the traditional CMDP. And if I make R equal to 1, then it becomes fully robust. Then nothing is known. But in this case, what I'm saying, there is a 1 minus R weightage on the nominal value and R weightage on the uncertainty. Okay. And then I am taking a Cartesian product for all state actions. So this is for a given state action and all state action. Remember that we need not know the knowledge of this or Q. I need to know the value of R, and I need to know that, okay, my uncertainty set is having this structure, and I'll be able to find out the optimal solution using RL. So this is my flow chart. So I will initialize the Q value for the state actions and the Lagrange multiplier. I will take an action. I will observe the cost and next state. Based on my observation, I will update the Q values and then update the LM values on two different time scale. So these two different time scale is basically kind of saying that, okay, if I, let's say there is an inner subroutine, I am fixing my, ideally what I should do is I'll fix my LM, solve the inner subroutine and then change the LM. Here I am doing the same thing, but I'm saying that, okay, I will change both of them parallelly, but one I will change slowly, one I will change fast. Okay, and it will have a same effect. So therefore, I am saying that update Q value in the faster time scale, update LM in the slower time scale. Okay, and then my algorithm looks something like this. So if you look at this, I mean, basically this, if you look at this, so qt t plus 1. So this is my q function for at t plus 1. So this is iteratively I am changing the q function. 1 minus gt is the learning rate, into old value, plus this is my observation, into gamma r max over s btst. So this is the term that is coming because of robustness. Uh, so this r into q. So this, because of this I am getting this term gamma r max over s btst. So this basically because of the worst case I am having this max, and then gamma 1 minus r vt. So this is the usual q learning that is coming because of this. So with 1 minus r weightage I am behaving like this nominal PSA, and that's why I am using the value function. And with r weightage I am behaving like a this with this uncertainty, and therefore to deal with the robust, I am using robustness, I am using worst case, I am using this max over s. That gives me the worst case value function. Okay, I'm not going into the very detail of it because of time limitation, but and that is the kind of the more intuition. And then I'm changing my beta, which is the Lagrange multiplier, within in a slower time scale. So this is my fast time scale, this is my slow time scale. This is nothing but a gradient descent or gradient descent sort of thing. And this is the q learning. If you have a like knowledge about normal q learning, you will see that this term is exactly similar to normal q learning when my r is equal to 0. Basically r equal to 0 means no robustness, but when r is non-zero, then this is the extra term that I am adding, gamma r max over s vts. This is basically giving me robustness. Okay, now for this algorithm I can prove that again there is a contraction mapping kind of behavior and there is unbiased estimation also. So because of this contraction mapping I am good, and I can prove that my q function iterates, it will converge to the optimal q in an almost sure manner. Almost surely it will converge to the optimal q function for a given LM. So it basically says that if I fix my Lagrange multiplier, then the q function iterates. So these are my iterations. This will converge to the q star, that is the optimal q. And second result says the same thing can happen for LM also. So the Lagrange multiplier iterates also, which is basically following this gradient descent routine, that will also converge to the optimal beta star in an almost sure fashion. And therefore these two together, if I add these two results together, I get this, the q function and the LM iterates converge to the optimal R2 CMDP and optimal LM almost surely. So QT is almost surely converging to q star beta star. So this is the kind of the main result I wanted to highlight, that here if you look at the algorithm, it does not require any knowledge of lambda, any knowledge of uncertainty set. It just needs to know the value of r, and with that I am able to prove that I am basically going to the optimal solution almost surely. Also, almost surely is basically in a limiting sense, as the number of time step goes to infinity, then I have a convergence like this. So this is the this is the main result, which allows me to say that, okay, and through q learning based robust q learning based solution, I can find out the optimal solution. So again, a complexity study. Uh, because of this operation, if I compare it with the Q learning, then there is an additional factor order of S that is coming here. In Q learning, we have order of A because if you make R equal to 0, then you only have this, which is VT is basically max over A, sorry, mean over A, Q, ST plus 1, comma A. Okay, so this operation is order of A, but here I am incorporating this operation for the robustness. Gamma R max over S VTS. So now VTS is max over A and mean over A, and then this is again max. So A into S, so it becomes order of SA. So there is a, again, as you see, I mean in the last work also you have seen this robustness has its cost, that there is an extra additional computational difficulty. Here also we see the extra computation part comes into picture, whereas storage wise both the non-robust and robust are same. Storage wise there is no problem, but computation wise it's increasing by this much. And to deal with that, we have proposed another algorithm. I will not go into the detail of it. It's basically some sort of this bound on this. So this term I try to put an upper bound, and that will allow me to do it in order of A operation. So we are able to come up with this bound. Then using this bound, this basically this is a term that can be computed offline, and it becomes a order of 1 operation. So this term we are able to give it a bound, upper bound like this, because of which it can be computed offline outside. And then the next algorithm looks like this. So if you compare these two, this was the fast RSA TSA RQ, that is the robust Q learning based update rule for task allocation. This is max over SBTS, and this is the heuristic that we have proposed. So this term we have kind of upper bounded by this term. Now if you look at this term, this is max over S, mean over A, this. These values are known, so it can be computed outside, and this is just a summation. So now in the last algorithm, it again goes back to order of A because of this entity, because this is mean over A. So now if I compare Q learning and this, it has robustness, but the computation is also same, storage is also same. Only what we lack is the convergence guarantee. This algorithm, we have proved that it will converge, but this algorithm we cannot prove it is converged because it's a heuristic and we have used a upper bound. So there is no guarantee that it will converge to the optimal solution, but the computation is much reduced. So some simulation results, as I increase the value of R, we see that it becomes less sensitive. I mean, it becomes more robust, and in similarly this deadline violation is also preserved, and some more simulations, that is comparison with some other algorithms to show that our algorithm is better. And here we have considered more practical scenarios such as mobility of users and inter-arrival time. Also we have taken Pareto, which is more general than exponential distribution. So to conclude the second work, in traditional CMDP based policy is highly sensitive to perturbation, and therefore we propose two algorithms. One is the optimal one. However, there is an increase in the computational complexity, and the second algorithm, which reduces the computational complexity and still preserving the robustness, because in simulations we see both of them perform similarly. And we have done theoretical and simulation study to show that it will converge to the desired optimal policy. So thank you. That was all.
Hello, sir. Yeah.
Yeah.
So I think, okay, so it's a very interesting and insightful, and the work you have done in different publications, so it's very interesting
Thank you.
and I mean, um, very deep research actually, because so much of mathematics and all is involved. So we got few questions from the registration form we shared. But sir, all are actually not related to your work
Okay.
directly. So it's some are actually in general work, it's general questions. So
Okay.
uh, yeah. So maybe I'll ask one by one. Maybe we can spend some 10 minutes time, then we can
Yeah, sure,
close
sure.
this. Yeah. Okay. Um,
Sorry, I exceeded the time little bit. Maybe the second work. I mean, the problem was I could not present the second work if I am not presenting the first work
yes,
because
yes, yes,
these are
yes.
related. So that's why it took some more time for me to finish.
It's fine
Yeah.
actually, sir. It's fine actually. So few general question maybe I'll ask first.
Mm.
One question is like if for example we develop this model, okay, we develop this model and then we want to and you told like in NS3 you did the simulation and all. So I am not from this particular background, but
Mhm.
after doing that simulation and all, then we are getting that this is our very optimized model and we got all the calculations and all. Then if I want to do a edge deployment, so how to proceed actually?
If I have to do a
Do
mm,
something like real time deployment, for example, some edge device or something. So how to
okay.
proceed in that actually? So do you have any kind
So
of board or yeah?
yeah, so very good question. So let me go to the slides and give the answer. Mm, so first of all, my slides are visible, right?
No, sir, it stopped.
Oh, now
Uh, Not
not coming.
visible.
Ah,
Yeah, it's visible.
mm. So first of all, this NS3. I mean, this open source NS3 based NB-IoT framework. So this is a narrowband IoT system. The code has been written by, as I said, by some university. So this NS3 is kind of a simulator which will mimic the real life scenario very closely because many of the, for example, that fading, that what will be the fading between the source and the destination, those kind of measurements are taken from reality. I mean, they have done real experiments and then take the data and put it in simulator. So that is in that sense, NS3 is very close to reality. But in reality, if I want to deploy, as you asked this question, that let's say I want to test this solution in a real world scenario, it can be done. Let's say you can do it in some, let's say, Raspberry Pi. Raspberry Pi is one IoT device, so you can sort of create a test bed. You can, if you have a Raspberry Pi, in that Raspberry Pi you can kind of create certain tasks and you can do it there. So Raspberry Pi will have some CPU, which is definitely lower end CPU than your PC laptop, and it can so and edge computing environment is also nowadays available. It's little costly, but edge computing environment is also gradually becoming available in the market. So that also can be, we can test it in that also. Otherwise, a laptop or something like a workstation can act like a edge computer where we have a more high-end CPU. So if you create a network using, let's say, something like a Raspberry Pi, or there is something like a ESP32 board that is also available. So with this kind of boards, you can create a network, and your laptop also laptop or workstation can act like a what to say, act like a edge computing, mobile edge computing server, and then you can test the solutions. So that
Okay.
will be, I think, a practical implementation.
Okay, great, great. Okay. One related questions they ask is that like what are the main challenges, for example, from simulation to hardware setup? So what are the different challenges is there, like real-time constraint or maybe limited memory processing or unpredictable wireless conditions? So what are the different challenges are there? So that was one question actually.
Yeah, that's also a good question. I cannot answer it fully because I have not tested the solutions in
Okay.
real hardware. But what I will say is, in real hardware, the main problem is this kind of assumptions in real world may not hold. For example, in this work, we have assumed that this is Poisson random variable, and yeah, if I go to the assumptions, yeah. Poisson random variable, and exponential service time. Channel condition is good, bad with Bernoulli. First of all, these distributions may not hold in real life. So the assumptions under which your theory is developed may not work well in real life cases. I mean, that is one of the challenge. You need to tweak it properly to make it work. And this is one of the biggest challenge, in my opinion, that the assumptions that you are taking for your theory to hold may not work in practice. It may the arrival process may be very different from Poisson, or your channel condition might be good and bad with equal probability, or with some probability. Those kind of assumptions also may not hold. And second thing is, for example, this formulas that we have written. No? So look at this formula B by Rm. So this B by Rm is the channel capacity. So channel capacity means the maximum rate at which you can send. But in real life, this quantity can vary with time, and you will not be able to send at Rm. You will be able to send at much slower rate, because channel capacity is the maximum rate at which you can send. So because of this value will also be different. But otherwise, this FM, JG, JB, and this kind of behavior will not create much problem. But this RM and these assumptions and yeah, this kind of things might be little problem. Your delay also formula, I mean, it may not act like the one that you have taken to develop the theory. So these are some of the challenges.
Okay, so I think it's very interesting. Yeah. We received one question from chat box. I think
Mm.
from YouTube chat. I think we can take that first. So
Okay.
the question is, can RL agents train in simulation reliably transfer to real world environments, ensuring safety?
Can you repeat the question
Yeah.
again?
So question is, can RL agents trained in simulation reliably transfer to real world environments, ensuring safety?
Yeah, that is actually a very important research direction that people are like pursuing nowadays. That is safe RL. So there are many research going on this RL, reinforcement learning, but safe RL is one of the area in which people are working, and it is extremely important for scenarios like, for example, self-driving car. In self-driving car, there are works where RL based algorithm are like used, but uh, it may happen that because of your algorithm, because there is inherently some exploration mechanism that are present in RL. So because of this exploration and all, it may happen that you go into a state where there is a collision of two cars. That kind of things may happen. So that is basically taking you to a state where it is basically becoming unsafe. So there are some works going on, research works definitely on this safe RL, and yeah, I think it's an ongoing research. So it's a very important topic that the in so in this kind of papers generally people talk about that. Okay, this is my RL algorithm, but I want to make sure that it becomes in a safe region. So these are the states which are kind of unsafe state. So in my optimization problem, I should ensure that my trajectory should not touch these states. So these kind of things are being handled mathematically as well as in simulations. And yeah, yeah.
Yeah, yeah, that's actually the his one part of the question is like if we train one RL agent in the simulation, for example, your algorithm, then can we reliably transfer to the real world environment? That is also one part of his
Oh,
question.
okay. Yeah, as I said, these kind of problems will be there. I mean, the answer to
Mm.
this question is again same, that if you do it in
Yes, yes.
simulation, probably this kind of assumptions might be there. I mean, this kind of assumptions you might incorporate it in your simulations, because in simulations I can generate traffic using Poisson, but in real world it may not be Poisson. Or this channel condition also in simulation I can make it good and bad with some probability, but in real life, those kind of things may not occur. So these are the challenges that you will face if you want to transfer the RL algorithm for simulator to real world.
Okay, okay, okay. Thank you, thank you. So then we move to this earlier questions. So one person asked. Okay, so for example, here, like you are going to do the optimization using RL.
Mm,
Now you need some optimal policy and all. Now
mm.
the thing is that can we do the same thing because you showed the difference between this DP also. Okay, dynamic programming
Difference
also.
between.
DP also dynamic programming
Mm,
compared to
mm,
this RL and the
right.
process. Now,
Mm.
so can we explore this game theory based approaches or because graph theoretic based approaches because we can assume this network as a itself is a graph. Each node will act as a like that. So can we explore this kind of optimization techniques as well?
So, to answer the question, so first of all, game theory based approach definitely can be taken. So, let me explain it here. So, this is one, let's say I just extend this diagram. This is one MEC server and some IoT nodes. Let's say there are another copy of this, another MEC server, and again some IoT nodes. Okay. And then what will happen is, let's say uh, now the user can choose to go here or here. I mean, either it can do it here locally or it can go here or there. And let's say each user is taking their own decision. In that kind of system, what will happen is each user will try to optimize. So here it is centralized. As I said, this is centralized. So if I make it a distributed system where all the users are taking their independent decision, then it will become a game where each of them is playing against each other and each of their objective is to optimize their own system. So each of them will try to optimize their own utility and then it will become a game. And when there are several players who are doing that, so then and that kind of thing is known as SG. So when and it's called stochastic games. So if we extend the concept of Markov decision process to multiple agents, here there is a single agent. So when there is a multiple agent and each of them are playing, trying to optimize their individual utility, and then that kind of system we can capture using stochastic games. It is there. And yeah, so one can refer
Okay,
to the literature on stochastic games. So that
okay,
is there. Graph theory, I'm not sure. Graph theory means sometimes these tasks are modeled as graph. That can be there. So there is something called this, I think, directed acyclic graph (DAG). So sometimes what happens is there are tasks has some interdependency. So here we are assuming that one task comes, you are serving it. Another task come, you are serving it. But task also might be like a graph. That this is one task, T1, and then there is T2, and let's say there is another one T3. Now T1 and T3 maybe you can execute together, but T2 you can execute only after T1. That kind of relationship may be there, and then if the task becomes more complex, but that kind of things also can be probably handled. I have not done it, but this is also another interesting extension. The task is like a graph.
okay. Interesting. Actually, yeah, yeah. So one very basic question we received. So that is yeah. So that is from because we know these communication systems are very maths intensive.
Mhm,
So so since there are like lots of linear algebra optimizations techniques. So I'm summarizing his question.
mhm.
Probability. So for a student, undergrad student, I think he is. So what is the right mathematical foundation for that to deep dive into this kind of works?
Right mathematical foundation is first of all, I mean, for example, if you want to work with this kind of systems, it's a stochastic system, and then you are trying to optimize and trying to find out some solutions using RL or MDP. So I think the right foundation is you have to have a good knowledge of probability and statistics. That is the first thing. And after that, probably optimization. So if you have a good knowledge of probability statistics and some amount of optimization, you can learn these topics. That is my thing. I mean, maybe you may not be familiar with these things like MDP, RL beforehand, but if you have a good knowledge of probability and little bit you know about optimization and some amount of linear algebra, mostly probability deep knowledge is required, then you will be able to understand this topic, and it will require some time to understand, but if you have a good knowledge of probability, you will be able to grab this topic. No problem.
Okay, okay. So, I think, okay, I think we can. I have one question. Just I was going because I am not, as I mentioned, I am not from this particular background.
Mhm.
So apart from this robustness, you mentioned robustness to like that task arrival rates. I think you mentioned that. So what are the different uncertainties are there in this particular scenario?
Robustness to task arrival is one. Another uncertainty can occur from channel statistics. That channel also can be uncertain. That
Okay.
when I say that, okay, let's say it is good and bad with probability p. Now this p also can be like within a set, that
Hmm.
it may not be fixed quantity.
Okay.
So that is also another source of randomness.
Oh, another source of randomness.
Mm.
Okay. So
At least for
the
this problem, these are the two sources. For
uh,
other problems, there can be more.
okay. So now, if we have to like design something like very from maybe like if we want to handle these different uncertainty, so we have to taken care of all uncertainty and then we have to create the model. Okay, like
Hmm.
that. Okay.
But it will not be that hard. I mean, in the
Oh,
same
okay.
model, you can do it.
Mm-hmm.
I mean, it will not create additional complexity. If there are two
Mm-hmm.
sources of uncertainty also, it will
Mm-hmm.
give you same amount of trouble. I mean, the trouble
Okay.
will not be more.
Okay.
Yeah.
Okay. And typically, what will be the model footprint of this particular whatever you have designed? So what MB or in terms of MB, maybe 100 MB or 50 MB. So
So basically, you want you talking about the size of the code.
size of the code. Yes, yes, yes.
The size of the code, maybe. Yeah, maybe few, I mean, less than 1 MB probably.
Okay.
If you take
Okay.
the file size, because the code is not that hard. I mean,
Yes, yes, yes.
as you see the algorithm, that pseudocode,
Yes,
it's
yes.
not that
It's
hard
not that hard.
to
Yeah,
write
yeah.
line 100 lines, 100 200 lines of code. Using that, if you write in Python, you can find
You
out.
can write. Okay. And the last question that is from my side actually. So maybe it will be helpful for others also. Like in I work in speech, so speech and NLP kind of thing. So now we have some kind of benchmark. So for example, if I want to do speech recognition, then if I want to build some algorithm, so we have some kind of benchmarking in that. So we have typical database, and then we have some kind of websites where actually we'll get like what different algorithms people have built and what are the typical error rate and accuracy people have
Mm.
reported compared to these papers. So is there any kind of benchmarking where we can compare our algorithms, widely used different algorithms through some kind of benchmarking? So
Uh, uh, if you talk about robust RL, then these are, I mean, robust RL basically, these, I mean, in this kind of problem, that these mobile edge computing networks, the robust RL, not much work is done. I mean,
okay,
so there is only one work before us which did this kind of work. I mean, this robust, but so that also we have highlighted. Yeah, this is the paper.
hmm,
Uh, my screen is not visible, right?
not
I think I
visible.
have to,
Yes, possible.
no, I have to share. So, entire screen. Yeah. So, yeah. So here now it is visible, right?
It's visible now.
Yeah, so this is one work that was done previous to a similar, almost, I mean, there was no constraint and they don't care about the, I mean, they don't cater to this sorry, computation cost. They didn't reduce. I mean, in our case, computation cost also we reduced. But this is one work that was done before us for
Hmm.
this edge computing certain and uncertain transition probability. Other than
Hmm.
that, for edge computing, we have not seen any other work. So therefore,
Okay,
that is one thing. And but if you talk about RL algorithms, I mean, if you talk about normal MDP, there are many works,
okay.
and that's why we have compared with some of the works here. For example, this CTSA. CTSA is
Hmm.
something like a constrained MDP without robustness, and this is
Hmm.
also another work with which we have compared. This is
Okay.
called like equal splitting. So I mean equal splitting or maybe fractional splitting. So some fraction are going here, some fraction is going there. So so with this some algorithms we have compared. I mean
Okay.
this is also one of the algorithms that is kind of existing, but again these are not robust. But with robust algorithm, not much work has been done.
Okay. Okay. Yeah. Thank you. So I think we don't have any. Yeah, we don't have any questions.
Okay, okay,
Yeah, we don't
okay.
have any questions in YouTube chat also. I think yeah. So it was very interesting, and like how RL can be used for different this kind of task scheduling for this wireless communication. So it's very interesting. So I think our audience got some idea, like especially we just more focus on these undergrads, and so they can learn something from your talk. And if
Yes, yes.
anyone, yeah, if anyone interested, maybe directly they can contact you for
Yeah, sure,
any
sure.
kind of
If anyone is
yeah.
interested, they can
Yes, yes,
email me.
yes,
And
yes.
I will also say that this kind of works are also nowadays more important for future wireless communication system
Mm,
in 6G. There is a huge push for AI/ML based like algorithm development for 6G or 5G systems. So, uh, I mean, in future there will be a lot of scope for
yes.
doing this kind of work. If anyone is interested, they can definitely contact me. And thank you also for your encouraging words.
Thank,
It feels good when this kind of works are being encouraged. And yeah, so thank you,
thank you,
Shishir, for that, and
thank
others
you.
also.
Yeah, thank you, thank you. So I think we can, Sasanka, we can close this. I think.